In this video, we're going to talk about an abbreviated version of Chapter 14, which deals with linear regressions and correlations. So I want to describe the basic concepts that we're going to discuss in this chapter. We're going to do some examples, and then we're going to move on. There's going to be some material that is important in this chapter, and we're completely skipping Chapter 15 for the Spring 2020 course. But there's some topics that I think that are worth exploring. The two main topics that I want to talk about in this chapter are linear regression and correlation. So the idea with linear regression and correlations is that we're going to look at some data set, and I have a set of 8 points. There's nothing special about these points. They have integer coordinates, although in general they don't need to be. But we have 8 points, and what we're going to do is we're going to draw a scatter plot of those 8 points. So in other words, we're going to just put all those 8 points on a graph. And what we want to know is there a single line that can best describe the data? When I say best, what I want to do is we're going to use what's called the method of least squares. So I want to jump to a graph that has these 8 points on them to give you an idea of what we mean when we say method of least squares. It's 1, 4, 2, 5, 3, 7, 4, 7, 4, 10, 5, 12, 7, 10, and 7, 12. These are the 8 points that we were working with on the worksheet. And this is these points graphed just on a normal XY graph, so just on a Cartesian plane. And all we're going to do then is we want to figure out what's the line that's going to best fit the data. Maybe it's this line. That looks pretty good, right? Y is 5 plus 0.9x. That's what the line is. This brackets just tells you the domain of the line. We'll come back and we'll talk about domain in a second. 5 plus 0.9x looks pretty good. It's kind of partway through the data. About half the data is above it, half the data is below it. It has some pretty good characteristics. Maybe 4.7 plus 0.9x would be better. I don't know, but let's see. So maybe 3 plus 1.5x, that also looks pretty good. That tends to go through the data. Again, it's a little more data is below it than above it, so in that sense, maybe it's not great. What about 4 plus 1.25x? Okay, that's also a good one. I want to point out that this idea of half the data being above it and half the data being below it is not what we mean by best fit. It turns out that what we're going to mean, and we'll prove that this is the actual line of regression that we'll talk about soon, but what we mean by best fit is that if you were to look at the deviations of the data points from this line is going to be called the regression line. And if you were to look at the deviations of these points, that's how far they differ in the vertical direction. So in the vertical direction here. So if I pick this point, drop a line straight down, and measure that distance, that's going to be how much the data differs from the regression line. So if we put all of those values there, what we want to do is we want to minimize these values. And the way that we're going to minimize the values is that we're going to compute what these differences are, square them, add them up. That's the quantity that we want to minimize. So this is going to be called the method of least squares. So the method of least squares turns out to be a Calc 3 problem. This is something that I have my Calc 3 students do every time I teach Calc 3. And it turns out that we get a nice solution that we can just use. You don't need to know any calculus, let alone Calc 3 for this class, but it turns out that you get a nice solution, and you have the regression line y hat equals b naught plus b1x, where b1, the slope of the regression line, is given by this formula. So what you do is you add up the observed values, so this is xi, minus the mean of the data set x, times the y values, y sub I, minus the means of all the y values. So you take that product for each of the values, x1, y1, you get some number, and then x2, y2, you get another number. You add them all up until you're done. And then what you do is you divide by this sum, which is going to be the sum of the differences between the x values and the means. I want to point out that this quantity s sub xx is related. It's very close to the standard deviation, right? This is the exact quantity that you look at when you look at standard deviation. In fact, exactly what it is it's the variance, the standard deviation squared, times n minus 1. We'll make that precise a little later. At least you'll see a formula that involves that. Anyways, this is the formula for B1. B naught, B0, is then going to be just the means of y minus B1 times the means of x. And then our regression line that we're going to get is B naught plus B1x. So, for example, the data set that we have, the data set of those 8 points that we had above, gave us the first spot as our x value. So we had x equals 1, 2, 3, 4, 4, and so on. The second spot in those pairs are the y values. And then given our set of x values and y values, you can compute the means of the x's, the means of the y's. This tells you how to find s of xx and s of xy. I said that backwards, s of xy and x of xx. And then you can take the ratio of those two to get b1. And then once you have b1 and once you know the means, then you can compute b naught. And so I've kind of ran through all the numbers here, and it turns out that our regression line is going to be this line right here, y hat. Y hat, by the way, is the predictor variable, the predictor value, I should say. It's the value that's predicted by the regression. But our regression line is y hat equals 3.513 plus 1.48x, just rounding everything to 3 decimal places. And what we can do then with that predictor, with that linear regression, is we can kind of infer, we can make predictions about what's going to happen to some value that's not in our data. So let's say that I want to know, I didn't give any context for these data points, and I still won't. They can be whatever you want. But let's say whatever that data represents, I want to know what's going to happen when x is 6. And so what I can do is I can think about, well, what's the regression line going to look like when x is 6? And it turns out that if you plug in 6 for this formula, in other words, if you take your regression line and plug in x equals 6, it spits out that y hat is 10.403. These points, it turns out that we can use this linear regression to predict what's going to happen when x is 6. So if we were to plug in 6 into this data, we would end up with 6 comma 10.403, and that's a point that's exactly on the line there. Okay, so that's a point that's exactly on the line. So that is how this linear regression works. I should point out that I had the wrong line in here in the previous video. I had 3.153 instead of 3.513, but all the relevant information is still the same. Okay, so if we turn off the deviations that we have, get rid of our predictor variable for x equals 6, this is what the plot should actually look like. Two last things that I want to say about linear regression. One is that not all data fits a linear regression. So for example, if you were to have a data set and the data fits around a circle, or maybe the data has some other shape, clearly modeling it with a line is not going to be the best idea. Okay, so that's the first thing, is not all data fits a linear regression. There are more complicated regressions like quadratic regressions or even exponential curves, so lines of best fit, using the least squares criteria. These are not things that we're going to talk about in this semester, but these are things that exist, right? So you can fit data to whatever curve you want. Lines are the easiest. The second caveat that I want to say is that if I were to take some data point or some data set, and let's say I have, I don't know, however many data points, it doesn't really matter, and then we talk about our linear regression, it's tempting to draw the line through those points. We can kind of, maybe that's the right slope, but maybe let's adjust the y value. And then it's tempting to say, well, we don't know, this is all the data that we have, but maybe we can make some predictions in this space, right? Maybe it turns out that we can say what's going to happen in the far future, and that's a bad idea. It turns out that linear regressions are really only going to be useful for us between let's zoom in a little bit here, but the only values that we want to keep, the only values where this is really going to be useful in making predictions, is between the x and minimum and maximum x values that we have. So we can ignore really all the other data points outside of this domain, say from this looks like our minimum value and our maximum value if the x value were to extend a little farther. Any x value outside of that region, we should find another model. This isn't a good model to predict what's going to happen when x is, say, over here. Okay, so we need to be very careful about domain restrictions when we do linear regressions. All right. The next topic to talk about is what's called the correlation coefficient. And as we just discussed, not everything fits, not every data set should be fit to a line. And what we want to know is if we have a data set that's fit to a line, how good of a model is that? Okay, is it a very strong linear relationship? Maybe that means that all the data points all basically lie on the same line. Maybe it's a line with a positive slope or a line with a negative slope. Maybe it's a weak linear relationship, so there's some relationship between the x and y value. So if you have a larger x value, maybe you know that on average you have a larger y value. That's some information. Maybe there's no linear relationship. Maybe there's no way to predict what the y value should be based on the x value, right? So if you have just random data points, knowing the x value tells you nothing about the y value, right? There's just no relationship. And maybe there's nonlinear data sets. So maybe this is an example of, say, a quadratic. This kind of looks quadratic in its model. So anyways, let's assume that we have a data set where a linear regression is appropriate. What we want to do is we want to measure how good of a model is that linear regression. In other words, how strongly does that fit the data that we have? And the way that we can do this quantitatively is with using what's called the correlation coefficient. This correlation coefficient is going to be called R. And before I tell you, well, R is always going to be a value between -1 and 1. If R is equal to 1, that tells you that basically all the data lies on the same line. It tells you exactly that all the data lies on the same line and that line has a positive slope. If R is -1, then all the data is on a line, but that line has a negative slope. So if R is positive, the line has a positive slope. If R is negative, the line has a negative slope. R is always going to be between -1 and 1. And here's a good chart that I found that describes all the different values of R, right? So again, if R is 1, that's going to all be along the line. If R is -1, that's also along a line just with a negative slope. If R is 0.8, that tells you that there's a strong or a high correlation between the data. If R is smaller, then you get a weaker correlation. If R is 0, this tells you that knowing the x value is not helpful in predicting the y value, and then likewise for the negative values. Okay, so this is R, and the closer R is to 0, the less helpful a linear regression is. The closer R is to plus or minus 1, the more useful a linear regression is. So now comes the usual caveat that correlation does not necessarily imply causation. Okay, and I love this comic from the comic strip XK, I think it's XKCD. I think it's XKCD, not XCKD. I'll have to fix that. That's a funny little typo. Anyways, so I love this comic strip, and I'll let you look that over. But now that we have a good intuitive understanding of what R is and what it means, now we can talk about a formula. So I'm going to let little s sub x and little s sub y be the standard deviations of the data sets for x and y. And again, here's the relationship between the standard deviations in these quantities s sub x and s sub xx and s sub yy. S sub yy, just by the way, is defined similarly as s sub xx, and I define it, I actually write it out below, so there's a context that it comes up in on page 3. Anyways, so what we can do with this formula for the correlation coefficient is let's take our data set that we have, which is those 8 points, 1, 4, 2, 5, and so on, all the way to 7, 12, and we can compute the different quantities. So in our example above, we computed s sub xy to be 37.75. We can quickly compute the standard deviations to be 2.167 and 2.915 respectively. And therefore R, remember that there were 8 data points, so n is 8. So R is going to be 37.75 divided by, this is 8 minus 1 times the standard deviation in x and the standard deviation in y. So we divide by those 3 quantities and we end up with 0.854. And so if we go back up to think about what that means that there's going to be a high positive correlation between the x and the y values. It's not a perfect correlation because not all the points lie on the same line, but it's a high or a strong positive correlation. And again, it's a positive correlation because the slope of the line is positive. Okay. What we're going to do next is I want to show you how awesome R is. This is another place where R is super powerful, and all the techniques that we're talking about have a very nice implementation in R. So we'll look at all the R code that's built in that makes all these problems a breeze. So I've already loaded x and the y values into R, and you can plot these x and y values and you'll get kind of a graph here. So you get this kind of plain graph. And what I want to do is I want to show you how to mess with this plot. And one of the things that you can do, and one of the things I like, is just to make the points a little larger. So if I have the default size as 1, if I make the size 1.3, you're going to notice that these points here are going to get just a little bit larger, a little bit easier to look at. And another code that you can do, another thing that you can do is change the point character. And the default is 1. You can change it to, I think you can go from 1 to 30. It's something like that. But you can figure out all different sorts of characters to make as your points. I have no idea what 8 is going to be. Here you go. So you get little stars. I really like using point character 16, which is solid points. Okay, so it's the default value 1 is just the hollowed points, the empty circles. These are the filled in circles. And the last thing I like to do with my graphs when I use this is I like to take and add some color to it. So if you don't know, I like the color blue. That's why I write everything in blue. I just like how that looks. So if I were to write this kind of dark blue, which is blue 4, that's one way that you can add some color to it. If you want to figure out a list of colors that you can find, just type colors with open parentheses, and there's 600 some odd colors that you can choose from, all in alphabetical order. Okay, so anyway, so there you go. One other thing that I like to do with this data is, of course, we do have our x and y values, but sometimes it's helpful to work with what's called a data frame. And so what I want to do is I'm going to define a data frame as df, and if I were to list out x and y, it just gives us the x and y values. But a little bit more useful tool to look at is this data frame. In this data frame, what it does is it kind of groups together the data in x and y. In order for this data frame to be defined, you have to have two lists that are the same length. And what it does is it tells us that we have 8 points, and here's the 8 points. Okay, and so that's one thing that we can do there. Now, to show you how nice and simple this is with R, and I'm going to add these codes in to the Google Doc that I have on Canvas shortly, but to show you how nice these codes are, let's just run through the example that we had. And what we want to do is we want to find a linear regression that fits these 8 points that we had. So we want to not only find the line of best fit, we also want to graph it. And it turns out that the code for that is we're going to use LM, which stands for linear model. And there's lots of things that we can do, but what we're going to do is I'm going to have LM of y compared to x. And it's important that you put the y values first. So the values that you're trying to predict, right, your predictor variable, you put in first, and then the other variable goes second. And if you do this, what it does is it spits out those values that we had before, 3.513 and 1.148. And so this tells you exactly how to find the line of regression. So our linear regression line is going to be y equals 3.513 plus 1.148x. Okay, so that's the line that we had. And lastly, if I want to graph this, all I need to do is type AB line. And what this is going to do is, you know that a line is determined by the y value of the y-intercept, which is 3.153, and the slope, which is 1.148. So 3.513 and 1.148. And if I were to type this, what's going to happen is that if we go over to our plot, it's going to put this regression line right in the middle of our plot. Okay, and there's our regression line. That's exactly the same picture that we had on Desmos, and that's it. That's all you have to do to get the regression line. The one thing that I don't like about this regression line is that it gives you this misleading quality over here. Really, this regression line should stop at 7. It shouldn't say anything about values bigger than 7. It shouldn't say anything about values less than 1. All that we're going to do to use this is make predictions between 1 and 7, never outside that region. Okay, but that's the AB line. And so that is really all you need to do for linear regression. LM, by the way, stands for a linear model. Okay, so that's the linear model. You can also do the general linear model, which is sometimes talked about and something that I talk about in the worksheet. This gives you a little bit more information about stuff that we did not get to talk about. Okay, so chapter 15 has to do with analysis of residuals, and you get into some of these concepts, but LM is good enough for us, so that's the code that I'm going to put on our Google Doc. All right, the last thing that I wanted to talk to you about was the correlation coefficient, and that also has a very nice, straightforward formula. It's literally just COR, all lowercase. You're comparing X and Y, and you get out 0.8535 or 0.854. Okay, whatever our value was that we had on the worksheet, that's where I got this value from. You can do it by hand just as easily. Okay, but everything here is right there, just in that COR function. And if you wanted to get the correlation coefficient squared, it's as simple as you think, right? You just take the correlation coefficient, you square it. That's your R squared, which relates to that. R squared is a formula that comes up again on that third page of the worksheet. Okay, and I was not going to talk about the third page of the worksheet. It's just there for you to view. It's optional material. Okay, but that's it.